Hello everyone, I'm David. In the previous tutorial you saw what generative adversarial networks are and how you can run and train a network. In this video I will show you an application case where you can use deep learning and in particular GAN to facilitate pet-driven motion compensation for FTG dynamic pet brain studies. Let's start with the presentation. So why do we want to do pet-based data-driven motion correction? To answer this question, we need to go to our previous work from our group on non-invasive absolute quantification. Our software, Aqua, utilizes the synergistic structural and functional information from an integrated pattern system to produce a cerebral metabolic rate of glucose maps. The pipeline is fully automatic and is meant to help clinicians in the diagnosis of epilepsy. So why in clinical medicine, if we want to help clinicians in the diagnosis of epilepsy, we use these glucose maps and we compare the glucose maps of patients with the glucose maps of a control group population, healthy population, in order to identify much more easily some abnormal foci in your brain that could be possibly a big expression of epilepsy or other diseases. Aqua was developed for an integrated pattern system, but it would be more valuable if we translate this pipeline to a PET-CT, which is more widespread and less expensive than PET-MR. To perform non-invasive absolute quantification, we need first to extract the image derive input function. The input function, called also delivery function, describes the concentration of unchanged, so non-metabolized tracer compound in arterial plasma as function of time. If you want to know more about input function and how PET works, you can check the link below. But for now, we're going to limit to say that this input function is fundamental if you want to perform absolute quantification and also kinetic model studying. To accomplish this task, the key points of the pipeline are extraction of the blood pool region to derive the input function, motion compensation, in fact, the patient moves the head in the scanner, causing artifacts and error in the estimation of the glucose maps, and partial volume correction, derived problem related to the resolution of the PET data that needs to be corrected. The void delineation and the partial volume correction can be performed with a PET-CT and MR protocol without simultaneous PET-MR. The motion correction part of the pipeline is the challenging task to replicate for a PET-CT system. Why? Let's find out. In an integrated PET-MR, sparse MR navigators are required to detect motion, and we can apply the motion vectors to align the PET images. In the PET-CT, we can only register directly the PET images at different time steps to compensate motion. But this will not work. Why? Because as we can see from the graphs, the activity distribution in PET frames during the scanning is changing, while in MR navigators, image information does not change drastically. Standard registration algorithms do not work if the images have not enough structural and feature information. To overcome this problem, we need a transformation to achieve constant activity over time in PET images as well. So, for this, as you can see from the graph, so we are looking for a technique which does a smart Photoshop, preferably automatic. For this reason, we use GANs. As you have seen, they can convert drawings to realistic painting. But people have already used this kind of architecture to convert low-count images with high-count images in low-dose images for PET data. So we wanted to do the same for the early part of the dynamic PET series because they resemble low-count images. Based on this, we developed PANDA, PET navigators using deep learning. The model is available online. You can check the QR code. And we also were going to see the model online together later. How does it work? First, we use the MR navigators to detect brain motion. We apply the motion vectors to the PET images and we align low count PET data at different time steps with a high count PET reference frame. We train the CGAN to perform the transformation low count to high count PET data. And finally, we can apply this model to a PET-CT system. We are going to register the processed PANDA PET images for motion compensation. This was the available dataset made of healthy volunteers, and also we perform artificial data augmentation for training the GAN. Ground truth arterial input function and metabolic glucose maps were available for this control population. We tested our method on validation data, excluding the training data. These are the results. PANDA can pre-process PET frames at times greater than 2 minutes of the scanning, while the structural information inherent to very low count images, less than 2 minutes, is insufficient to generate an acceptable results. Nevertheless, our previous study suggests that for early time points, the motion magnitude tends to be negligible, and so the results it's not so compromised by the missing information. We validated PANDA by deriving first the image derive input function and compare results without motion correction and with motion correction based on not pre-processed PET frames and PANDA PET frames. We achieved less than 1% deviation from the ground truth with our technique, and after deriving the image derive input function, we also derived the glucose maps and compared them with the ground truth. The group analysis showed that the absolute percentage difference was less than 5% for the glucose metabolic rate of maps. So this was the final slide of the presentation, and as you can see, we derived high count PET images from low count PET images to perform registration. This model is available online and on GitHub, and you can download the model, and you can also, if you want to train this model, you need high computational power. So if you have a gaming computer, a gaming fixed computer, you can download this model, and you can also try to run this model on public dataset. If you don't have a low count or high count PET frame dataset, it doesn't matter, because this model is very general and it takes 3D images. And for example, we use also this model to derive, for example, T2 images of the brain from T1 images of the brain, but you can apply this in general in any way you want, either in the medicine field or in a non-medicine field, because GANs is just a network and is their application, they are quite general. If you have a low count PET data dataset, you can actually launch the inference of our network, as you can see from the pipeline here, and you can also download the weights that are available online in order to launch it correctly. If you want, you can start our model, and if they're here in the web page, there are available all the description related to how to use it, and you can also take the scripts that we wrote as reference if you want to develop new networks and if you want to dig on different topics. Now I'm going to show you how I run it, this model. So I open my Anaconda script. I'm going to the network. For the sake of time, I'm not going to launch it in real time, but I already launched it just a few minutes ago to save some time for the reference, for the inference. So you don't have to download the weights, you have to go into the folder where you had downloaded the program, and if you launch the pipeline that is available also in the GitHub page, you can derive from a low count bad data, high count bad data. So I'm going to show you the results that I obtained from launching the pipeline. So I open my program to visualize the images, which is 3D Slicer, and 3D Slicer is also a nice program and software where you can use if you want to analyze medical images and also perform different operations such as segmentation and registration automatically. And I kindly suggest you to read about it and to use it if you're interested in the field. So this is my PET image, and after launching the inference from the pipeline that you saw online and also from my Anaconda prompt, as you can see, if this is the high count PET frame that I generated. And so after we ran this inference, we were able to register each frame all along the scan, and then we were able to extract the image derive input function. So let's go to this last slide of the presentation, because I want to thank you for your attention, and I hope that this presentation was interesting for you, and also I hope that you would star my GitHub, the GitHub webpage, and please, if you have any question, you can write me on GitHub, and also you can go to the hybrid webpage and write me an email to the address to my page in hybrid page. Thank you for attention, and put a like also on this YouTube tutorial and to the other tutorials from the other PhD student. Bye.